Welcome to the videos on data converters. In this video we are looking at analog to digital converters, some examples of successive approximation ADCs. This is a ninth part of A to D converters. We are considering a successive approximation ADC of 3 bit. The number of bits are 3. The VFSR assumed is 8 volt. The LSB happens to be VFSR divided by 2 power n, which happens to be 1 volt. The input voltage considered in this case is 4.65 volt. Here we are writing the transfer characteristics of an ideal ADC. So as we know that the LSB is actually 1 volt. For every 1 volt we have made the corresponding output voltages. You can see for 4.65 the corresponding digital node should be 101. So for 4.65 we are supposed to get 101, because for 0 to 0.5 volt it is represented as 000. From 0.5 to 1.5 it is represented as 001. So similarly, having a code length of 1 LSB, the input voltage of 4.65 will be represented as 101. So let us try to identify how does a successive approximation 3-bit ADC will give a code of 101 or some other code as the input as we just move from one clock to other clock. So upon receiving the start signal, the MSB bit B1 is made 1 by the SAR, that is successive approximation register. The DAC output is given by V reference multiplied by, this is B1 which is 1, 2 power minus 1, plus B2 is 0 and B3 is 0. Only MSB bit is made 1. So as per this we're going to get it as 4 volt. This is what is 4 volts here. Since 4 volt is, this is the reference voltage what we are looking at, which is 4. It's not reference voltage, it's actually the input voltage. The input voltage is 4.65. The output of the DAC is 4. Since the output of the DAC is less than the input voltage, the SAR retains the bit 1 for the logic 1 for bit B1, and in the next clock pulse it immediately makes the second bit B2 also 1. The DAC output corresponding to that happens to be, as per the equation, 6 volts, but 6 volts happens to be more than 4.65. Now since the output of the DAC is more than the input, SAR register immediately makes B2 as 0. So you can see now the B2 is being made 0 now. So once B2 is made 0, now it will be again 1 0. Once B2 is made 0, immediately SAR register makes B3 as 1. So now you can see B3 has been made 1 here. So this is B3 1. So B3 has been made 1, and by making B2 0 and B1 is 1 and B3 is also 1. So as per that 101 we'll get it as 5 volts. Now this is the 5 volt what we are having. So this is 5 volt. Now since this 5 volt is also more than 4.65 the input voltage, it immediately makes the B3 also 0. So B3 happens to be now made 0. Why this B3 is made 0 means because the successive approximation register, upon giving B3 1, actually got 5 volt as the DAC output. Since DAC output is more than the input voltage, the SAR register is forced to make that B3 as 0. Now B3 has been made 0. Now since B3 has been made 0, so we are having an output voltage. Now let me just change this. The output voltage is now, whenever we made B3 as 1, so B3 1 has actually resulted a 5 volt. Since 5 is more than 4.65, B3 is made as 0 by the SAR. As the bits are over, so the ADC will flag a EOC signal. The final digital code happens to be 100. In the previous transfer characteristics, you can see we have actually shown it as 101. So this is the error that you're going to get in your successive approximation 3-bit ADC for a 4.65. The actual representation would have been 101, but we are actually getting it as 100. So this way we're going to get an error of 1 bit, so while representing the digital equivalent of the binary of an analog voltage. Now let us consider the same example of 4.65 volts implemented using a 4-bit resistor. So 4-bit ADC, 4-bit ADC. Now since it is 4-bit ADC, so we have plotted the transfer characteristics, and we are supposed to get for 4.65 1001. So in the previous slides we have seen that for same 4.65, instead of getting 101, it has been represented as 100. So there was an error. So let us try to find out if we increase the number of bits, does that error will going to reduce or not. So whether we're going to represent 4.65 by the ideal characteristics of 1001, or will it be different? Now, as it was done in the previous example also, upon receiving that start signal, the MSB bit P1 is made 1 by the SAR. The corresponding output voltage is 4 volts because VFSR is 8. So now you can see we are getting it as 4 volt, and this is your MSB bit is made 1. Since MSB is retained as 1, immediately after just after T1 clock pulse, the B2 is also made 1. Now you can see the B2 is made 1. The corresponding DAC output happens to be 6 volts, which is more than 4.65. So naturally, SAR will make this B2 immediately 0. So along with that, it will make B3 1. So B3 is made 1 and B2 is made 0. So now you can see we have 5 volts. Since this 5 volts is also more than 4.65, which is this 4.65. Now, since it is since the DAC output voltage is more than 4.65, it will immediately make B3 also as 0, and it will make B4 as 1. So now B4 has been made 1 now. You can see now the B4 is made 1, and now we have B1 is 1, B2 has been made from 1 to 0, and then B3 is also made from 1 to 0, but we have this B4 is being made 1. So since when B4 is made 1, we have the voltage 4.5, which is less than 4.65. The SAR retains that B4. Now after the 4th clock pulse, because no more bits to be appended, no more bits to be made high, the final output voltage is actually 1001. So that's what we are getting. The final code happens to be 1001. As we can see in the as we saw in the previous transfer characteristics, we are supposed to get for 4.65. So the bit was supposed to be 1001. So we are exactly getting same 1001. So you can see the previous 3-bit representation identification of an equivalent digital code for 4.65 using 3-bit. There was an error, so we are supposed to get to 101, we were getting 100, but as the number of bits is increased from 3 to 4, we are actually getting the exact representation of 4.65 as per the ideal transfer characteristics. So this way we can minimize the amount of error in representing any analog voltage to its digital equivalent if we have more and more bits. So it's always necessary that if we are handling very small voltages, it's always necessary to have a larger number of bits so that we can properly represent its digital equivalent if we have more number of bits.